change fellows this year. Like last, but not least, series of seminars devoted to climate change communities. It's the middle of the climate change community, and I'm from the civil, construction, environmental engineering department. It's only fitting that I wear my construction. So the about this series is, we're able to react to a lot of people from different places that we make on a daily basis. Over in all, there's not a lot of conversation about bees or pollinators or plants. There's conversation about climate change. And today, I heard Dr. Sankar will be giving a discussion on climate change can affect things like water supply, water demand, and water quality. Sankar at Tufts University in 2001. He served as a postdoctoral researcher at the International Research Institute for Climate and Society, and served as a professor in our department since 2005. So the presentation line for discussions, and then we'll have a short thing where we can take these questions. So welcome, Sankar.
Really nice to see that the first initiative in terms of this community thanks for this opportunity, everyone, and thanks for coming. I have designed my background is on climate applications to put it in so most of my work is on either in climate variability, seasonal, for example, forecast, or climate change projections, moving water, energy, and perhaps I did some work on EG as well, looking at in-stream flow restorations and other things. So my goal here is to not go in depth on each one of them, because each one of them is a paper by itself, and rather provide a broad perspective of what the seasonal example forecast as well as climate change projections can do, and how we can do, how we use of it in the context of water, energy, and perhaps ecological sustainability. That's how I'm motivating here, and so anywhere around 30 minutes, and hopefully you can have a dialogue after that. So to bring context here, so there are two aspects of climate. I mean, one is the climate variability, that is a structure variation, like for example, it is also changing. Like, ENSO, LE, sun oscillations, or PDO, they report the variations in our seasonal climate. And also, there are aspects which is primarily time scale projections, meaning, so like, for example, 10 to 30 years, or perhaps even more, to the end of the century, we have projections. Those are all projections of that we get from perceived growth in terms of the carbon dioxide concentration. So there are two aspects. One is the variability, and another one is the change. And I work on both aspects in terms of looking for opportunities for applications. So the first one is primarily on the water and energy management. So they really provide an important context for supply as well as the demand. And so if the weather is, like, for example, very cold, then obviously the power is going to be higher. And then also similarly, context in the context of the illustrations, like for example, how when we build a reservoir, naturally we are going to change the flow regime of the hydrology. So how to restore can we forecast in terms of restoring the flow? So the first aspect of the talk I'm going to primarily focus on the aspect of the story, primarily like forecast. We have climate forecast and how we can do that in the context of water and ecological management. And the next one is the baseline time scale. I'm going to not talk primarily in the context of 10 to 30 years, and because I want to see some I want to see some usefulness of these projections, and that's where I belong. And not just the longer time scale projections alone, we may get in water supply, but on the other hand, you see USGS water use data. We have been really improving our water use efficiency. So there's that associated in terms of looking at the projections and how we have developed ourselves. So I'm trying to spin both aspects of the story in terms of talking about longer time scale, 10 to 30 year time scale planning and capacity expansion projects, and where these things can provide information and how we can bring all of this together to us better. I mean, in the kind of adaptation, there is a lot more out there. I take more of a quantitative approach looking at the problem. So, to start kind of an overview of what I'm going to talk about on the first one. So, climate information, like for example, translation, and last conditions, like for example, either water equivalent or you have antecedent soil moisture conditions that primarily drive your water supply, or in other words, the input into your reservoir, and provide critical information on how we can manage the reservoir system. So, a short-term planning, like the seasonal context, think about, for example, the east reservoirs by April 1st, that we take for Paul's sake, we do 1.5 is the operation group curve. We need to have every single year, but that's not the story in the context of western reservoirs, where we take over supply and deficit from 1 year to another. So they are on bigger reservoirs. So they need the forecast or more of variability over the longer time scale. Whereas here we are more in the context of seasonal forecast. But the thing is that most of the storage systems over the years, they are also smaller for capacity. So we need to look at here is that the aspects also make a lot of information on how forecast can be made useful. So it's not just the forecasting skill alone. What are the systems like what is the demand versus the total storage capacity? They play an important role in the context of management rather than just looking at the forecasting skill. This is where I belong. Looking at the phase of the skill of the forecast with the system configuration. So in this case, I will start with the one script on the forecast, the forecasting skill. So if you look at most of the seasonal forecast, most of the forecasting skill, 2 to 3 months ahead forecasting skill, only in the context of winter season, because that's the time when it's so peak. I mean, the linears are not like peak. So if you see here for 2 different forecasts, the way from that, and the skill differs from model to model. And also they differ depending on what sort of conditions we are in. So in the top panel, where we have the 2 months of skill using a linear condition, this is non-linear conditions. All the white are basically conditions where you do not get any skill at all. In other words, it is really insignificant. You can drop it up. But when it comes to the neutral conditions, all the skills, the higher the correlation by here, so neutral conditions, most is most vanishing, or it is other. So the context here, what we are talking about here is to forecast better during linear conditions or non-linear conditions, but during neutral conditions, if you tend to swing, in fact, some of the models they don't go exactly opposite. So how we combine multiple models instead of reducing the forecast. So what we did in this case is that we try to evaluate the skill of the model based on the predicate. In this case, this is winter, and the Inflow is the primary influencer. So we combine multiple models and look at the skills. And in general, what we found is that those models will reduce the uncertainty. In other words, to say, it reduces the aggressiveness of the confidence of individual models. To put it in a different way, if you are in a condition, model will say that percentage probability of above normal precipitation. In this case, whenever you are having El Nino, the model should go to that is 90% of the time. It doesn't have capacity. So when you come to model, it reduces The aggressiveness or overconfidence of the model, thereby we get a much more reliable forecast. This goes into forecast calibration literature, which is the reliable forecast improves when you use multi-model forecast. And it's kind of more or less, established within the literature that multi-model forecast in general improves the reliability of the forecast by reducing the overconfidence of the individual models. So something that we did, and why it is important, because my argument here is that the implementation forecasting still is negative for some model, and we go with one model. What's happened? We are going to do this case. It's that usually the model will be grown up. So they use that uncertainty by bringing in more models. I think the super studies to make single model that can also provide the reduced uncertainty rather than just create one single model. So it's a lot of here, but we try to assess the conditions because during winter, our primary drivers is the El Niño southern oscillation. I think I have done quite a bit of work on user forecast in the context of reservoir management. So I'm presenting those detailed results on those things, but I can tell more of what I learned from it. So understanding from that is your initial conditions of the reservoir is not constraining the season. There is no use of forecast. In other words, you have knowledge you're taking account. How much you spend maybe like $6 the next month? How does it what you're going to get as salary for the next month? So this is the slide. So the forecast is not going to be really helpful if you have lots of storage capacity and very small. And if you don't have very good skill in forecasting, the storage to demand is very small. That means within your reservoir. So very small storage capacity, your annual demand is very high. Then in that case, forecast, even if it is marginal still like 0.5, it's going to be useful because we are going to capture that change the stream flow potential from normal to above normal or normal to below normal to your various operational strategies. So for example, if it's going to be below normal, you'll be able to go for proactive restriction. Like you may be able to introduce three different audience restrictions, voluntary, mandatory, emergency, which happened only like 1980 to 2002. So we are able to go for some proactive restrictions if, for example, the wind is going to be dry. That means, like, for example, it happens in non-linear conditions. Condition is very easy. And where the initial conditions of the reservoir also matter. We have combined both of them. So I'm quite a retrospective analysis on what forecast can do and have. There are two systems to storage capacity to demand, and another aspect is whether the wire is cooling or not. If then there is water that is not cooled. If you hydropower, if the reservoir is cooling, it's a lot of option. You're not putting that water into the line. So a good, well-calibrated above normal forecast, in other words, reliability of the forecast that we improve from multi-models to for normal conditions, is going to result in very good conditions for hydropower. And that is a good below normal, well-calibrated forecast. It's going to be useful for energy for proactive restriction and good for trading, and I think this is more common in the context of the Western US where people trade between different uses. So what we did this work is so without the slides or anything, I'm giving you the storyline. So I also thought the importance of run models and making it available for the public. That's a very important aspect. So one thing we have done is when Ryan was there, we have created an integrated water portal. And so the water portal, what it does is that every month, like around the middle of the month, it automatically downloads the forecast from IRI, that's the place I work. And because it's got multiple models, I can go for multiple models, the reason. And automatically converts it into forecast. One is a statistical model, and another one using land information system. It is a suite model, land-based model, and convert that one into inflow forecast for reservoir location as well for upstream gauges. So these forecasts are automatically archived in the state land office data. And one can, go say, for example, okay, they want to release operating policy 700 feet per second downstream Falls Lake, down Jordan Lake. They provide those releases and find out what probability of meeting the target story, like 2.5 for Falls Lake and 216 for Jordan. So you can run these scenarios. So we have the proactive something. We have water, but when doing the dry area, the probability of meeting the target story, that is like 2.5 or 216, is going to be really low. You're not going to need because the change in signal potential. So that will give you the signal. Our gas is going to be down. But the point is, four is better than no forecast. The average flow. Better than that, and that we have done that over and over 6 days or 7 days. Because the climate forecasting field also, we have made the initial conditions of the land surface to map for the next season. So going into, and it is better than that of the climate policy. That's the key point. So, because the conditions are known to you, there is no answer. I mean, in other words, the initial conditions are known, means it is more of a model-based information. So you can use that one to forecast for the next season. So we have Falls Lake and Jordan Lake, the management portal. You can improve the forecast if you forecast. Forecasting is never. If you run your model on your desktop, it's never going to make any difference of really validating real-time conditions. So this is a real-time forecast, and it is updated. And you can go and play retroactive scenarios and other things. So this is a good education too. I use it for my class too. So so what would have happened if you have allowed this release? What would happen if you have done this way in terms of managing the system? And so we have this based and matter-based information system for available. It's easier to run it on a larger spatial scale. So available for many different ways. These are all upstream because the virgin basins are the either the Hessidian basins. They are all impacted by storage or groundwater pumping. So you'll be able to get inflows and compare your forecasting skills. In other words, to say these are all, inflow get, otherwise. That's the only way to look at it. This, see that for some of the large basins, the appalachian solar, it's pretty good because like you have better initial conditions. So the stage of the land storage is as well, not just the climate forecast. So you combine these two on a continuous basis to make the forecast. In fact, the information system we are working on a different paper comparing the primary forecast with the product, the emergency product, or the last one of the real-time products that are available. So we are comparing that one. So I think there are a lot of opportunities in understanding both the land conditions and providing conditions which are very important and critical for water supply management. The population that we have, that's another important point that we need to see here. Most of these reservoirs, they are designed, very I think, we don't really get we have information many large reservoirs. So the point is that it was not a particular need. Now our population over the site grown 500. So one other needing another thing is going back, supply of water. So like some of the drought we have, it is not purely the climate induced, but also the demand induced. The demand is going to stress the system at one point or another. So they withdraw around 5 to 60 million gallons per day. Now it is almost 62. So I will design capacity is around 7 million gallons per day. So unwind, you have to cross that threshold. Even if you don't cross that threshold, plant-induced drought is going to come back to us and contact. So we have a proactive approach to assignment, and that's the clear point. We learned it's not just the skill alone. You have to look at both aspects of the story. Moving so what applies to our energy side. So I'm not a civil engineer or anything, but I talked to some of those people. So one that, if you look at the forecast, that's the critical thing for street forecast. They are very critical for the like example, the southeast. Most of the heating meter, of course, nationally cooling is primarily using, of course, the electricity. So provide information, and so this is condition of the covariability on precipitation temperature. So if you look at it, like Orange Valley is highly correlated with the winter. For the Midwest, the Indian correlation is and negative. So in the context of water and energy management, so this nexus on power and energy to put it in a different way. So you hydropower feeding into the power sector, and you have temperature demand forecast providing information on the power demand, and you also have the precipitation forecast providing the water supply. So you bring these two things together in terms of how it can, different scenarios. Like for example, go through this in a little more detailed way. Like if the correlation between pressure and temperature is, for example, then if you are having precipitation, then the temperature is also abnormal. In other words, to say it's going warm winter. So you really have that much power demand, but the extra water in the reservoir, which is too loud, which is resulting in large humidity. So the opposite condition in the supply is that really happens during non-linear conditions. So the temperature is also below normal. In other words, it's a cold winter. So this and the energy completely in the opposite spectrum. So your supply is way lesser than that of the demand. So the key question here is that how you use these forecasts in terms of improving the system management. So that's the key point that we are talking here. There are conditions, so like for example, decisions such as fueling, like for example, in our area, typically on the state, you need to have a coal supply available, so you don't run out of coal. So these are all the management strategies that you can have. And so we look here showing the additional on the power demand explained over the country using. So this is using observed temperature. I mean, compared to precipitation, forecasting temperature, forecasting field temperature is much better. So what you have here is the additional variability. This is over a period of 30 years. So you can see how much this is for summer. Over that's where we saw that there is a significant field to be precipitation temperature. The additional variability that we are explaining is much higher. Obviously, all the northern places like not as we have that much additional variability. The demand on the power also is very less during the summertime. The same applies in the context of winter. So winter is a little bit tricky because just the power alone, if there is a partly oil-based cooling, oil-based heating over the northeast. So it's a substitution effect that we need to take into account. So it is less in terms of the role of temperature, but obviously it provides a lot more information. And one out of this exercise is that this is the role of temperature varying, and the suspect is becoming much more dominant in the context of winter. So Three drives water quality. I mean, this is the next application that we look at. Quality is more difficult. One problem is that you don't have that much data. So you have, 2 data points or one data point or 2. So we get to that level of sophistication, that level of comfort we get in quantity. Inflow is well observed. Most of the time you have to go out there and so total nitrogen and total phosphorus. These are the ones from the context of fish scale and trying to predict the oxygen. So see here is that the ability to predict J and what based on the climate forecast. So what we did was we tried to the previous month inflow as well as the next 3 months ahead precipitation and ran that month. Obviously, since the model is not continuous, since it's not continuous, we have to develop a continuous data model. So we tried to adjust the chill in terms of on the model skill as well. So this is the actual skill with the skill of the model. We get the overall skill on that variability that we explained. So see that some of the coastal waters might be good, and that's the place where you see usually good skill in forecasting sea flow too. So what goes is that there is a way to translate some of the stability of the skill in stream flow to quantify the nitrogen loadings as well as total phosphorus loading, which is critical in the context of what amount of loadings that goes into the estuary. So we can get an idea about how useful it is from other things like, for example, what quality trading that is between point source and non-point source that you can. But I think here is much more on the context of data. So in stream flow restoration side, so any of you must be familiar with the indicator of hydrology gas alterations. So what happens? Most times the peak is cut off. So for simple this is Roanoke River Basin, prior to water, and after the reservoir is fully in operation, stream flow variability is dampened for this. You have conditions pre and post. You try to look at their frequencies, how well they are mapped, and the indicators of hydrologic alterations are like 30 variables on the stream flow side, and it's not possible to, in other words, to match the annual maximum peak of your conditions because the purpose of the reservoir is to control the flow. So those things are impossible. On the other hand, we can optimization model to minimize the versus post condition. So we are able to exactly match, but you can try to minimize that. So we try to run this experiment in so Philpott Lake actually has a hydroponic state on the blue basin. So that one, the line is the circle marker. So we consider five different variables in 35. That's not possible. And also we primarily started to monthly because we're forecasting context, you know, only the monthly forecast. So you want really is to maximize for hydropower. So the number of mistakes that we pre or post in this case is very like the correlation factor that is on the operational policy. This is the most important thing that we learned out of this exercise. That your BCD. So B is basically for into some fix on the water supply, and primarily for managing the ecological benefits. And E is for the ecological benefits, but we are trying to meet the demand of water. So with B, there is leaves D out, even that we really questionable. On the water supply side, can allocate the additional demand for inflow. So these are very used here, compared to which is the middle gap. So the thing that what you need to know is that most this is the challenge is coming when you talk about Army code. It's in portal and we ran a couple of sessions and the institutional mapping comes in. My data is only flood control. I don't care about the water supply. So the dialogue here between is primarily under the mandate of Army and the key water supply as well as kind of power operators. So this is where the challenge comes in. If you can motivate the point, then you can make the forecast available at some point or another. The teaching takes at the institution level, and others has a challenge. I mean, that's true with the Bureau of Reclamation as well as in the West. So based on the kind of forecasting, we found that in general, forecast provides, because it's a monthly, we are still in monthly which helps us to release extra water to be minimize the kids. And to make this case from the perspective of meeting the knowledge with demand. And so to have the story on seasonal forecast, what we found was that in general, forecast is better at a time of. Then the skill comes from the climate cycle. This also comes from the initial answer. And it also needs to be mapped appropriately with respect to the system, whether it's storage demand is small or high, depending on that, it can vary a lot. I think these are the take-home points I learned. And whether the reservoir is filling. If the reservoir is filling, there is a benefits in terms of using forecast. And as the storage is similarly, as the demand increases, you're going to constrain, now your system to demand is going to go down. So you constrain the efficiency a lot more. So here, switching it on to the near-term climate change, so project with the institutions that we had, and the primary focus here is the 30 years coming to an end. So to motivate the near-term point, this is a big paper, and if you look at, for example, over longer time scale, like 100 years, then level of carbon dioxide concentration that is uncertainty really plays an important role. If you consider something like 10 years, the general is reduced, and this is where near-term climate change runs similar to the retrospective forecast that we used for analysis in 2005. CMIP 5, they have that. So these are all initial conditions on the SSE from 1980, and you have 30-year run. Similarly, every year updated SSE conditions, and they provide, for 10 years. I mean, this is still out there on the SSE count sheet, but in general, some of the things on scaling and other things we find more beneficial. So what you see here is that we developed is that we also predicted better compared to precipitation. So we do, from downscaling perspective, statistical downscaling perspective, we try to do correlation structure between precipitation and temperature, not just some of the downscaling approaches they go for just univariate, that is precipitation versus precipitation versus temperature. So see here the Bureau of Reclamation product that is widely used as the JC canonical correlation regression. We found that our ability to preserve the probability of precipitation observed and to observe precipitation temperature. And you see here in context of the cross correlation, how well it is. So here, the red line here is the observed cross correlation over the entire U that having significant correlation. And these blue lines, they are basically your raw runs, and the grams are basically again the downscale, univariate downscale one. In the downscale ones, when you try to look at the cross correlation, it doesn't switch. So we analytically that the correlation in general finds as that what is predicted by the GCM doesn't switch. So that approach in general, it slightly shifts it to what's observed because it has the multivariate downscaling approach. It observes the cross correlation structure in the observed and I mean, why? Because if you're assuming your land surface model, that's important role in terms of point operation. If the temperature is not well quantified, when precipitation is available, then it will be your similar values are going to be wrong in terms of the solution state. So this plays an important role in the context of integrated surface water groundwater model. So this is a very interesting figure that inflows into Jordan Lake. The rate observed flows and the percentage of flow from wastewater treatment plant from Pittsburgh. So what do you see? You see here when the flows are very low, on the very axis, how much percentage is coming from just a treatment plant. So the 40% of the inflow in the lake is treated water. So we don't need to worry about water. So the key is that the return flow from the water treatment very important during drought conditions. If you really reduce the, in other words, you go back in conservation, this can have a feedback effect too. You cannot return that much flow into the income. So we take longer in terms of recovering from the storage condition. So what was to quantify this one? How long it takes? So if you go for some commonly used approach is that if you are in drought, you go for, I mean, this is at least life, not you have that much. If you concrete, what's going to happen is that naturally you will reduce the base flow into the stream. It means it takes much longer time for the reservoirs to recover. So your base definitely you have water from the active storage. So one was if you are concrete during drought condition just because you are in low water condition, it takes you 1.5 years for the system to come normal. If you pump, let's say that 50% of the deficit in terms of the inflow. So I think the peak might, of course, the volume you pump in peak, your time is also going to increase. So the key is that water both conjunction, that is both surface water and groundwater together. So this model is set up to provide the data, and this is a fully coupled surface water model, which helps us to the interactions between the water zone and the groundwater zone. I think it's pretty critical if you, without considering the interactive two systems, it's not going to be useful. On the climate side story, how about looking at this in terms of the demand? So if you, this is the most commonly used argument that we don't supply may go, but we have more efficient. So if you this is the USGS one, we they collect 1 in 5 years. And what for different users from 1950, the total withdrawal has remained more or less flat. In other words, our population has grown, we didn't withdraw that much, which we have become much more efficient. So then that means if the water supply goes down, will we be able to manage the system better? Drawing with reduced supply. The thing is that so the increase in withdrawal has happened over the south because the population has grown. The withdrawal versus the efficiency. So here, how public supply water usage efficiency has changed. This is from 1985 to 2005. The electronic in 2010. That's the period you have easy data available. So what gallons per day per capita means every year over the last record that we have from 85, 90. So basically 6 records. Basically 5 surveys not improve its efficiency. Okay, so if it is Massachusetts, every year they improve. If it is Northwest, like you take to Portland or Washington, every year they improve. So in other words, they are that means compared to 85, their consumption has gone down. That's why it is negative. If it's positive, then that means it has increased. So you make a scenario of overall green research, but in that picture there are some good. From in the study that in general, this is the other counties in general, they improve their efficiency. There are counties their efficiency is why? Not point. No, if you go for blue, you see what that's happening all over. So obviously, new systems, new structures, and you have less losses, whereas it's not the case in the case of rural. And then nicely relate this one with respect to most of the rural states as well. That probably they are good, but on the other hand, it's not the same story with all the other states. So I think that's the key take-home point here. And certainly on the irrigation side, too, it's the opposite. So in other words, so we are here is the year 2005 to 2010 to 1985, and this water is gone per unit. And here, if you see here, then that means per application in general has increased over to say that we drawn more water for irrigating. So what does it mean? Efficiency has improved. The states in general that has, I think it should go under any other rotation, but the key point is that that's the point. So states in general they improve their efficiency, and most improvements come from that of spur and drip irrigation systems. And the thing is the dominant irrigation system again, and so most of the efficiency we can attribute to the sprinkler system. So here, the point that I made is a lot more. I think 42 minutes. So the key is that climate provides information, and this is the events of look at the forecast in a retrospective way, not just skill, but clearly the system operation. Really has a lot of value, and we can learn. And I mean, touch upon this one in the context of near-term climate change. I mean, for example, we found that using factual information, like based reconstruction of inflows, is more useful than future planning, because the variability is better compared to what the climate model can do. So this is where the uncertainty reduction from little value as well as future really provides a scientific perspective on reducing the uncertainty on the low side. And there are also opportunities in the context of data analysis, like for example, most sensitive information as well as even observed people records. They can be useful for a model state in a field to example context, and that is useful in the context of climate change. And a lot of untouched areas in this area, which is like, for example, urban stormwater design, and it's an idea for us how we can look at it. I mean, I look from the perspective of climate to the, and I think that provides a nice story as well. So on the ecology side, I think one thing what we learned is that Secondly, considering root curves, operational policy, root curve changing means it's illegal for the Congress to change it. So, but on the other hand, simplification into the operational policy will provide additional water for maintaining the inflow. I think we can consider as an optimization key. And the last point I will stop. I'm a Windows user, but I still like the courses. You know, you can really come to we connect the dots by looking forward. We can only do it. But I think that is where the retrospective analysis and look back and see what we could have. And this is like Canada has a role in educating ourselves as on the public. And more importantly, I think for any product that we develop should not have computers. Okay. It should be there. The reason we use a routing, you know, based routing for driving from one place to another, it's to me this stochastic dynamic programming model. So basically, the same thing you can consider in the context of linking to forecast or I think there is, I can say that forecast is certainly better than no forecast. Equal forecast is easier to observe, but it is better than no forecast. And that I'll stop and we have a quick question. Thank you.